basically what I had last year, you know, when I just could not shake the cold. Okay. All right, we're ready. I guess it's okay. All right, this is, oh, did we find one like it?
Oh, no, I didn't read anything like that. I was wanting to ask about that notation.
Yeah.
For W. I was just wondering what that meant. Because I haven't seen notation like that. It was odd to me.
Obviously, it was something that I left off in the descriptor of it. Let me see if I can find. Oh, it's just like number 5.
Yeah.
Okay. So 5 and 6.
Just 6. I got 5. 5 was easy.
Okay.
It's 6 I had trouble because like I said, the notation for the first one.
Okay. All right. What 5 was here is a subspace W. It's the subspace of ordered pairs such that x minus y is equal to 1. Okay? And the vector space is all of R2. Okay. Now, what number 6 is W is a subspace. It's the set of all functions such that f of minus 1 is equal to 0. Okay?
I don't know, that just doesn't give me a whole lot of information right off the top.
Right. Okay, I understand.
Because the other one, there's a certain rule about vector spaces. It has to have a certain vector, and I determined that it wasn't in there because 0 doesn't equal 1.
What doesn't equal 1?
0.
Right, okay, right.
A certain vector. So
Okay.
that wouldn't be in there. So that wasn't a subspace. This one, on the other hand, I can't do that so quick.
Okay. Okay, let's maybe start with the vector space V. What does that stand for? That's the set of all continuous functions from negative 1 to 1.
So it includes 0. That's
Yeah,
correct.
right.
It is a vector space.
Yeah, and vector space is a vector space. Okay, the subspace, no, determine whether W is a subspace.
Yeah, exactly. If it is or not.
Okay. This would be the set of all functions such that f of minus 1 is equal to 0. All the functions that would give you that. That's a set of functions too. V is a set of functions, all continuous functions defined between 0.
So it's every function where when you plug in negative 1 to the function, it gives you 0.
Yeah.
Okay.
Now, is that a subspace? It certainly is a subset of the vector space V,
Right.
because it's functions. This is defined as that. Yeah. Is that enough?
Well, now I'm thinking, is the function, all functions, when you plug in negative 1 and the function giving you 0, is that enough to say it is a subspace? Well, it doesn't have to span. So yeah, right? It doesn't have to span the set. It just has to be a subset.
Yeah. But what? No, not subset. It is a subset. It needs to be a subspace.
Excuse me.
Yeah.
But it would contain 0 vector. I'm guessing it would. Because negative 1. The negative 1 would be like your x, right?
Yeah, that's the x value.
And then your 0 would be your y.
Right.
What section do you recommend it in?
Okay.
Wait, this is vector spaces here. Subspace.
Yeah. It's the one that says 4.3, I believe. And the two.
I guess kind of what I'm having trouble thinking about is how to test that W
Right.
to see if it's, whatever. Do I just plug in random functions where when you plug in a -1 for x, you get 0 for y? Or
Okay. Let's see, there was one here.
and when you plug 0 in for x, you get 0 out for y at any point.
Okay.
That would be my first question.
Basically, kind of the thing that Theorem 4.5 basically lists your test for a subspace. And there's just one other deal, and it is what you said before, that the zero vectors in it, and you've already said that was. So that part's done.
Problem.
So, okay. So basically you're saying if let U be any vector in W, okay? And V be another vector in W, okay? Then, and of course, these have to be true there. Then it doesn't matter what's going on anywhere else. At 0, -1.5, or at 2, or any other place. All that matters to be in W is if that criterion is met there. And if that's met for U, some function U of -1 is 0. And that's also true of V of -1 is 0. Then is U plus V also in W. Yeah, that would work there. And then the next one, yeah.
Multiply anything by
Right.
that, it would still be 0. Yeah.
Whereas if that had been f of -1 equal 1, or anything really other than 0, just the, yeah.
It's just that function notation.
Right.
Yeah.
Yeah. Okay, I'm putting this back in the right place.
And I hope yes on some of these is good enough answers.
It's what?
I hope yes or no is a good
Yeah.
enough.
Yes. And some of them is or is not would work, but yes or no would work too.
Okay.
And
Get
it?
you to work.
Huh?
I said, let me get you to work.
Okay.
Some of them were just unable to do without work, but
Right.
what work I do have. Like I need to write my name on it.
Now this is
S3.
this the last one I gave you?
Yeah.
Yeah, okay.
And you said you were going to add a couple of questions to it or something?
Possibly, yeah. We'll see how far we got yet. Oh yeah. Yeah, we'll see just how far we go in. Yeah. I've got it now. When Ashley came in this morning, it was raining pretty badly when I was driving in this morning, especially near Birmingham. It got clearer out here, but still was raining. And the roads were awful. I mean, trucks moving slowly, which I'm glad they weren't racing through it and stuff, but taking up both lanes. And there were 2 accidents on the other side coming in, and it was just backed up like crazy. And of course, every time there'd be flashing blue lights, everybody would slow down to almost stop, as if They're not going to give you a ticket if you're going the speed limit, or even half the speed limit. You don't have to stop, But I think what they were doing was rubbernecking, trying to see what was going on, So, and it happened twice. So I was really frustrated by the time I got here, running a little late. She was waiting for me, and I said, I think I gave you everything I have done already. And so we'll see how far we get here, and project how far we will get. Any questions besides the one we just did?
Where are we at?
It's on page 234, right at the end of 5.1. The dot product and matrix multiplication.
Alright, example 11.
Before that, the top of the page. We didn't do this, did we? I don't recall that we did. I put my mark there. The last thing we probably had was theorem 5.6, Pythagorean theorem.
Yep.
Yeah. Okay. Now, says it's often useful to represent the vector u. Oops, let me get my pen. Okay, vector u. I'm going to try to remember to do this. u1, u2, u3, dot, 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 up to u sub n. I hope they're still doing. Yeah. And Rn. Okay. As an n by 1 column matrix. And we've already talked about that. Basically, the way I just wrote it there is kind of like a row matrix. So that's represented as a column matrix. U1, U2, U3, dot, 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 down to U sub n. That would be U represented as a column matrix. Okay. What's that? Oh, yeah. We did this many times before. Yeah. In this notation, then the dot product of two vectors, if you had U being this and V being this, V1, V2, V3, dot, 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 down to V sub n. Then if you were talking about U dot V, you certainly couldn't multiply those two column matrices together because that's an n by 1, this is an n by 1, and they don't even multiply. Okay, so what we do, and this is what they're suggesting here, is write that as U transpose V. Yeah, you turn this one horizontal, and the reason you do that, if you turn the second horizontal, you would get an n by n matrix. And you don't want that as a dot product, you want a single number. So if you do a 1 by n by an n by 1, you get a 1 by 1, which is a number. And that's what you want.
You get a scalar.
You get a scalar, yeah. So this, they're just suggesting those are the same. Okay? And of course what that would be yuck. I'm going to write U transpose here.
You can write it out.
Oh, there it is. Let's just do it like this. Okay. That'll be U transpose then. And then when you do that, you get U1 V1 plus U2 V2. Yeah. And that's the dot product. Okay. Right. All right. So let's now do 11. Now that we've got the stuff. The dot product of these two vectors, here's U, written as a column vector 2, 0, and V, which is 3, 1.
Okay, so we're going to write U as a transpose.
Yeah.
U transpose would be 2, 1, or 2, 0.
2, yeah, but without a comma. I don't, when I go to do them horizontally, I always put comma, or not always, but way too often put commas
And that would be
because I'm used to doing them in vector notation, which
plus 0, which is 6. Okay.
6, right? Got it.
That was it.
How about these two?
E.
U equal 1 to negative 1. B equal 3 negative 2, 4. Yeah, pretty tough stuff, huh?
I know.
Now, many of the properties of the dot product are direct consequences of the corresponding properties of matrix multiplication. Later in exercise 85, if you choose to do it, you'll be asked to use the properties of matrix multiplication to prove the first three properties of theorem 5.3. Okay. Let's look at the linear algebra applied here. Looks like a good old bar magnet under some iron filings. Electrical engineers use the dot product to calculate electric or magnetic flux. You had that in physics? Seems like, were you in, which did you have in me, 201 or 202?
I had you for 201.
Yeah, it would have been 202. Which is a measure of the strength of the electric or magnetic fields penetrating the surface. Flux being a scalar quantity, field being a vector quantity. Consider an arbitrary shaped surface with an element of area dA, incremental area dA, normal perpendicular vector dA, with that A is now a vector. Electric field vector E, magnetic field vector B, the electric flux phi sub, is that an E? Yeah. Can be found, that's a lowercase script e, right?
Yeah. Or no, it's just a lowercase e.
Lowercase e, okay. I don't know why they wouldn't put capital E there. I would have, but that's okay. The electric flux phi sub E can be found using the surface integral, which we haven't gotten to in Cal 3 yet and probably won't get to, which would be the integral, phi sub E is the integral of E dot dA. In other words, a dot product.
So there's another integral we haven't gotten to yet.
Right. And phi sub M is your magnetic flux, and that would be the integral of B dot dA. It's interesting to note that for the given closed surface that surrounds an electrical charge, the net electric flux is proportional to the charge, but the net magnetic flux is 0 because the electric fields initiate at positive charges, terminate at negative charges, but the magnetic fields form closed loops, so they do not initiate or terminate at any given point. That means that the magnetic field entering a closed surface must equal that leaving. So if we had had that, you probably could have recognized some of that, but we didn't. Homework exercises, 1 or 3 or both, 5 or 7 or both, 9 or 11 or both, 13 or 15 or both, do 17, 19 or 21 or both, any of the odds, no, 23 or 25 or both, 23 or 25 or both. Do 27, either 29 or 31 or both, 33 or 35 or both. Any of the odds 37 to 43, any of the odds 45 to 51, 53 or 55 or both, 57 or 59 or both, 61 or 63 or both, 65 or 67 or both. Do 69, do 71, any of the, well, this is writing, so think through this anyway, 73. I don't know if that answers in the back or not. And then orthogonal vectors, which we have mentioned before, but not in this section, you would use that for any of the odds. 73, no, I'm sorry. Do 75 using the definition there, and then do any of the odds 77 through 87. All right, now moving to inner product spaces. Okay. Clear. Yes, I feel like it may not be, but it feels like my throat's getting even worse and worse. It's not getting any stronger as the day goes on. Okay, inner product spaces. In section 5.1, the last section we just did, the title of the chapter is inner product spaces, but we did length and dot product in Rn. So that those concepts, length, distance, angles, were extended from R2 to Rn. This section extends these concepts one step further to generate vector spaces by using the idea of an inner product of two vectors. You already have one example of the inner product, that's the dot product, okay? And sometimes that's called the Euclidean inner product, which, if you haven't chosen a paper topic yet, Euclid would be one, or Euclidean inner products, or how these are used, various possibilities. It's only one of several inner products that can be defined on Rn. To distinguish between the standard inner product, the dot product, and other possible inner products, use the following notation. U dot V is the dot product of the Euclidean inner product for Rn. This, however, strange as it seems, U V in angle brackets, and this may be why he doesn't use angle brackets here for vectors, because he's using this notation be the general inner product for a vector space V. General inner product for a vector space V. Okay? The general inner product is defined in much the same way that the general vector space is defined. That is, in order for a function to qualify as an inner product, it must satisfy a set of axioms. The following axioms parallel properties 1, 2, 3, and 5 of the dot product given back in Theorem 5.3 in the previous section. Blah, blah, blah. Okay. So here's where we go. Definition of inner product. Let U, V, and W be vectors in a vector space V, and C be any scalar. Okay. An inner product on V inner product, strange they use the preposition on V, is a function that associates a real number and this real number is U, V. So notice the angle brackets aren't designated any kind of vector anymore. They're indicating a real number. Okay? With each pair of vectors U and V associates a real number with each pair of vectors U and V and satisfies the following axioms. Okay? First, U, V must be commutative, same as V, U. We know that's true for dot products, okay? Because dot product has to fit all these two, okay? Number two, and this was from property 1 probably we had before. If you have U, V plus W, this has to be the same as U, V plus u comma w. Now remember, these aren't vectors. These are scalars, real numbers.
But I mean, this makes sense.
So again?
Because it makes sense. It's like distributing out the.
Yeah, and this will be your distributive property, right? Okay. 3. And that worked for dot products, by the way, too. C times u comma v is cu comma v. Now, what they didn't say, it would also be u comma cv, okay? That would have been fine too. You don't have to have it just on the first. Could have been on either one of them, okay? And number 4. And you sort of get that if you go back and combine it with 1, okay? Now, this is...
Number 4 is your favorite.
4, say it again.
It's your favorite.
Yeah, I imagine so, because it's dealing with the 0 vector, isn't it?
Yeah.
Okay. V comma V, okay, is greater than or equal to 0. Now that's not a 0 vector, that's a number. Why is that? Think of the dot product with itself.
You multiply anything by itself, it's going to be bigger than 0 unless it's 0.
Unless it's a 0 vector, exactly.
It's like squaring any number.
But V dot V would have been the magnitude of V squared. Remember, that was another definition of it. And magnitudes are always positive, and certainly if you square positive, you got it always positive. Unless one's 0. Okay? And this thing, this is the part you said I would like. V dot V, V comma V, is equal to 0 if and only if V is equal to 0 vector. Okay. Okay, a vector space V with an inner product is called an inner product space. So if you have a vector space that all these things work in, then that's called an inner product space. It has to be a vector space to be an inner product space, and it has to have all these things that happen in it for it to be an inner. Not all vector spaces this would necessarily be true. Whenever the inner product space is referred to, assume that the set of scalars is a set of real numbers. Okay. So example 1, the Euclidean inner product space for Rn show that the dot product in Rn satisfies the 4 axioms of the inner product space. I think we just about talked our way through all of those. Certainly, U dot V is V dot U. I already had that, but I'll look it up. The dot product of U with V plus W is the dot product of U with V plus the dot product of U with W. Just like we did before. Yeah, I think so. And so, yeah, we've said all those already as we went. Okay? But you can look at this and see how they solve these. Okay? The Euclidean inner product space is not the only inner product that can be defined on Rn, as we've said several times. Example 2 illustrates the that's coming up. I was going to say, no, that was inner product. That was example 1. Show that the following function defines an inner product on R2. I will clear this out, though I probably will need those, but I don't have room for them. Oh, man. So now I guess I've got to go back to using parentheses. U is U1, U2. What's that?
We used to use brackets on vectors and parentheses on numbers, and now it's backwards.
Yeah, exactly. Okay. And V is V1, V2. Okay. Now, here's, they claim an inner product space. UV would be U1 V1 plus 2 U2 V2. Certainly not a dot product. Awfully close, but it's not. It's,
Oh, that's what the game's.
yeah.
I did the dot product. That's like went with what I thought they didn't give us anything after that. And I was sitting here doing
Okay. Now,
not
what are they asking? Show that that function does define an inner product on R2. Okay? Well, first, what if you reverse the order? Then you would have V1 U1 plus 2 V2 U2. That's the same thing. So that works. So what if you had a third vector, W, this is a little tough because of their numbering scheme here. I think probably, yeah, you'll have a hard, yeah, no, they just throw it in there. Okay. Let's do that. U, comma, V plus W. Now, according to what they told us, this would be you through? Okay. Okay. This claims it's U, V, comma, plus UW. Okay. Now,
how does that work? Oh,
well,
yeah, that makes
okay.
sense. That makes sense.
Yeah. No. This is what we're wanting to show is true. Well, what would this one be? This would be U1 V U1 times V1 plus W1 plus U2 times V1 plus W1. Not 2, sorry. Okay. I don't think I need the bracket there. Okay. Do I? So that would be U1 V1 plus U1 VW1 plus 2U2 V2 plus 2U2 W2. Right? If U, V, and W are all two-dimensional vectors in R2, then this would be what it was, because yeah.
Yeah.
Okay. Now over here, this would be U1 plus U1 V1 plus 2U2 V2 plus U1 W1 plus 2U2 W2. Right? According to this rule, okay, V plus W would be V1 plus W1, comma, V2 plus W2, right? So U times, the first one would be U times V1 plus W1 plus 2U2 times V2 plus W2. And then when you break this down, that would be U1 V1 plus U1 W1 plus plus 2u2v2 plus 2u2w2.
And why
That's
is it,
what that tells you,
why is it 2 again? 2u2?
because that's what your rule is.
Oh, that's okay.
Yeah,
Okay.
that's your inner product rule here. Okay, different from your dot product rule. Okay. Now the claim is for this to be an inner product, this rule must be met. Well, let's see what this rule would do. U1 V1 plus 2u2 V2 by this rule, plus U1 W1 plus 2u2 W2. Well, let's see if this is the same as that. U1 V1 is the same.
2u2.
U1 W1 is the same. 2u2 V. Yeah. They are the same. So yeah, it's the second one that's met. Okay. Then you go through each one of them that way. The third one would be, I don't even remember the third one now. Oh yeah, the C, yeah. C times, yeah, U plus V, it better be CU writing this right. No, these should be angle brackets. I was going, yuck, this isn't right. V. Okay.
C, yeah, the C. I thought my parentheses earlier was the C, and that's what's going on.
Okay. Now, according to this rule, this would be C times U1 V1 plus 2 U2 V2. That's according to that rule. Okay. Now, what this is CU1 V1. Put commas where they shouldn't be. V1 plus I don't need parentheses there. I don't even know what that is. Okay. All right. Get this back again. C U1 V1 plus 2 CU2 V2. Okay. And if you multiply this out, you get CU1 V1 plus 2 CU2 V2. And that's exactly the same thing you've got there. All right. So the third one's met. The last one is that U plus V is greater than 0. Greater than or equal to 0. And yeah.
We assume that it is, therefore it is. Or we demand that it is.
No, U dot U. I'm sorry. I was going to say that's not necessarily true. Yeah, U, comma U. It's not dot. U, comma U. This would be U1 plus 2 U2 U2. Okay. Now, either you kind of have to do either U1 is negative and U2 is negative, or U1 is 0 and U2 is negative, or U1 is 0 is negative, U2, yeah. You really probably should do each of the cases, but no matter what you got, whether U1 is positive, negative, or 0, this is greater than or equal to 0.
Right.
This one's greater than or equal to 0.
Times 2.
And then the sum of those has to be greater or equal to 0. So it's taken care of. And the only time it would be 0 is if you want, what's that? Yeah, if you, and you, but C doesn't have to be 0, but U1 U1 and U2 would have to both be 0. All right. And then it would equal 0. Okay.
Of course, C has to be non-zero. Oh, no, it doesn't say anything about it not being 0.
Okay. Example 2 can be generalized. The function UV is C1 U1 V1 plus C2 U2 V2 plus, oh yeah, okay, they're just saying, if you're not dealing with 2 space, if you're doing an n space, then you can choose any multiples. Doesn't have to be 1 and 2. It can be 0.3 and 7/5, or something else like that. And that would be an inner product space. Okay. In exercise 89, you are asked to prove this. The positive constants C1, C2 are called the weights, and these are called weighting functions then. If any Ci is negative or 0, then this function, sorry, this function does not define an inner product. Okay, so in other words, all your C's there have to be positive numbers. Okay. The positive, okay, I kept saying, where do they say that? They say the positive constants C1 through Cn are called weights. Okay, if that Ci was either negative or 0, then that function doesn't define an inner product space. All right. What's that? Example 3. Let's go to example 3. Show that the following function is not an inner product space on R3, where U is equal to U1, U2, U3. Whoops, yuck. So used to doing it now, I can't not do it. Okay. Okay. And V is V1, V2, V3. All right. UV, this supposedly inner product space is defined to be U1, V1 minus 2 U2, V2 plus U3, V3. Okay. Now, no sweat doing 1 works. No sweat doing 2 works. No sweat doing 3 works. 4 is the one we have problems with, okay? Because what if U1 and V1 are both 0, and U3 and V3 are both 0, then and U2 and V2 are both positives.
Or if one of those is negative, it's fine.
Yeah, but if they're both positive, then hang it up, Jack. Okay? Because you're not going to get, wait a minute. Yeah.
It's as long as the middle term is larger than the other two terms
Yeah.
combined, it doesn't matter.
But now going back, remember 4 doesn't do with the 2, it does with just 1. U dot U or V dot V. Okay? Not dot, but, comma. Yeah, but still, so forget V. If U1 is, like you said, if U2 was greater than, significantly greater than U2 and U3, then yeah, the product of U1 by itself is positive, U3 times itself is positive, U2 times itself is positive, no matter what it would be, but minus 2 times that would be negative. So yeah, it would still be. All right. The counterexample, I use zeros, they use numbers as long as the middle numbers was significantly bigger. Okay. Now, let's do an inner product on M22 space, matrix spaces being your vectors. Okay. I'm going to go on and clear this just in case. I don't think I'll need it, but in case I do. Matrices take more room to write. Here's A is equal to, it's a 2 by 2, A11, A12, A21, A22. Some old vector matrix there. B is equal to B11, B12, C21. I'm sorry, B21, B22. Yeah. All right. There are matrices in the vector space of M22. Okay. Now here's the function that we're going to suggest is your inner product. AB A11 B11 plus A21 B22. A21 is what I'm trying to say, and I've written it wrong.
So B21.
Yeah, B21. Plus A12 B12 plus A22 B22. Okay. There's your inner product space, or they're suggesting. They say this function that does that is an inner product space, is an inner product on, I would say op, they keep saying on M2. Verification of the 4 inner product axioms is left to you. So you have to
So you have to make sure the axiom works.
Yeah, every axiom works.
Okay, let's start with 0, because that's the fun one.
Okay. Well, then you deal with itself. That would just be AA. So that would be A11, A11 plus A21, A22, A21 plus A. So no matter what the sign of this is, it'll be A11 squared, A21 squared plus A12 squared plus A22 squared. As long as those are real numbers.
All positive.
Yeah.
Or
Yeah.
zero, non-negative.
Not negative. Can't be. Okay. The rest of them, I think, fall into place a lot more easily. It's just getting so cold and stiff sitting there. Okay.
Seems like the hair is still on, even though it's colder than.
And, so I don't know what's going on. I wonder if just the hot water or whatever they use in the system isn't making it up here. And we're just recycling there. Finish. Sorry. Okay. Maybe you would think Rosie. Okay. All right. The others.
And he hasn't even seen my writing.
Huh?
He doesn't even want to see my writing.
Okay.
He thinks yours is bad.
All right. Let's see. Do you need to see the other three?
Nah.
They're pretty straightforward.
Also, 10 minutes. So you have some you have 10 minutes till class. So
Say this again.
10 minutes left.
Okay. Yeah. I
Not much
figured it
longer
was.
in the cold.
Yeah. I know, but I had to stand up just to move. All right. My eyes don't work though if I hold if the book's on my desk here. You obtain the inner product in the next example from calculus. The verification of inner product properties depend on the properties of the definite integral. So let's try this. I think that sounds ominous enough. We better get a new slide. Let f and g be real value continuous functions on the vector space C from A to B. F, G, real value. Yeah, example 5. Continuous functions. Okay? On the vector space. Now it's in the vector space. And this is set of all continuous functions defined from A to B. Show that f, g is equal to, oh, this is interesting, the integral from A to B of f of g, f of x, g of x, dx. That defines an inner product on, above they said in, now they're saying on CAB. Okay. Now that's your definition. So basically what you're saying here is that if you did the inner product of GF, it just changes order. No sweat there doing an integral. It doesn't matter. The integral of a product doesn't matter which way you multiply the product is the same. And by the way, G, F, and G are real value continuous functions, so their values are continuous, are real, they're not imaginary. So, okay, the second would be that F, comma, G plus H would be what?
We get hang beef in here.
Yeah, I know. Not spoiled. Okay. And again, integrals work. Yeah, they do that. The integral of F times G plus H would be integral of F G plus the interval of HG, and they both work.
They're basically just giving us a bunch of general examples, no real.
Yeah, nothing that's controversial yet that won't work well. I don't think they gave us any won't work that. And your zeroth one, the fourth one, C obviously will work all right. you put a C in front of this or inside either way. You pull it outside the integral and it still works. Yeah. Now the FF would be the integral of f squared, real valued functions, so it can't be any imaginary numbers there. So yeah, FF is going to be a square of a real number, and that's always greater than or equal to 0. So I think that's, and here they show those, that the integral of FG is the same as, or the inner product FG is the same as inner product GF. And FG plus H would be the same as FG plus FH. CFG would be CFG, man, which would be CF times G, which would be inner product, right? And these would be, yeah. All right. That wasn't as bad as I thought it would be, or it had potential to be. Here's theorem 5.7, properties of inner product spaces, basically. The old stomach's really doing a number now. So that was a nice little appetizer. Where's the rest of it? So U, V, and W, all vectors in an inner product space. Okay. Inner product space V. C is real number. Okay. Scalar real number. Okay. Here are the three properties. 1.
Anything times a 0 vector is 0.
0 vector times V is going to be the same as V with 0. Well, you know that from the first general rule, but then this is always 0. Not a vector 0, the number 0. 2.
These are the same, it's just missing the last one.
Okay. U plus V, W, which is a little backwards from how we've done it before, is equal to UV, UW, sorry, plus VW. That's old German carbide. Okay. And C3 is that U, comma, CV is equal to C times UV. Okay.
Those are just flipped around versions of what we had before.
Yeah, basically.
So what's the significance?
Yeah. It's what?
What's the significance?
Well, the others were the rules that we used to get them. Well, where did it go? There we go. Okay. These now properties that come from those rules, and basically it's just saying if the others are true, these have to be true as well, I guess. I don't know. And basically I almost said this one before. I said it doesn't matter where you put the C. It doesn't. So these are just other properties that these will have if they're vector spaces. All right. And then finally, let's do we have time for it? I think maybe so. Let's do definitions.
Less than a minute.
Well, maybe not then.
And I just saw the guys who are going to come put the projector in.
Right. All right. So we'll do the definitions, start with those next time. this is sort of, that's not a super long section. I think you can do so far 1 or 3 or both. 5 or 7 or both. 9 or 11 or both. 13 or 15 or both. I think stop there because we haven't gotten into the definitions will pick up the rest of those. So it looks like we'll get through 5.2. Will we get to 5.3? Probably. We might get started and we certainly won't get through it. So we'll get as far as we can. So I'll probably give